Hello, and welcome to the feature spotlight on the functional mockup unit import for Emulate 3D 2025. My name is Ethan Leib, and I am an applications consultant on the Emulate 3D team. This new feature will allow you to import models from other simulation packages, allowing you to make higher fidelity simulation and controls testing models. First, let's cover the basics on this feature. The functional mockup interface is a free, tool-independent standard that allows simulation software to exchange dynamic simulation models. This standard is currently supported by over 200 tools and is maintained as a Modelica Association project. When a simulation software that adheres to this standard exports a simulation model, it is called a functional mockup unit, or FMU. This is what we can now import into Emulate 3D. If you would like more details on the FMI standard, you can find all of their documentation online for free at fmistandard.org. Next, let's take a look at how this works in Emulate 3D. In this example, we will be leveraging some reference FMUs that are provided by Modelica. The first is called stare, which is a counter, and the next is called feed-through, which we will use to connect the counter to. Each FMU can be represented by any model visual by adding an aspect to it. We'll use a box for today. You can then find the aspect in the search bar at the top of the aspect viewer by typing in FMU. You will then see three categories: description, instantiation, and simulation. We'll start in the description category to select the FMU we want to import. The first one will be stare. Once you have loaded the FMU, you will see the description populate with additional information. Next, we can move on to the instantiation section, where we need to give the FMU a name. For this example, I will stick with the reference name stare. Please note that these names must be unique across all FMU instances. After picking the name, you have the opportunity to choose the parameters required to create the FMU instances. We'll stick with the defaults for today. Once you're happy with the parameters selected, you can click Create Instance, and now your FMU is in your model. We'll also have to create an aspect for the feed-through FMU. This will follow the same steps, so I'll go a bit faster this time. We start with a box, we select the FMU, we give it a name called feed-through, and we click Create Instance. Now with the FMUs imported into the model, we can connect them to other parts of your model using the wiring diagram. We'll pull in a wiring diagram controller using the wiring diagram catalog. Once you do, the wiring diagram will open automatically, and since you've already created instances of your FMUs, you will see them represented by blocks named after their visuals. If you don't see your FMU, you can refresh the wiring diagram by right-clicking on the controller. You can think of each FMU as a black box, where you connect their inputs and outputs to other parts of the model or other FMUs. Here, we'll connect the counter output of stare FMU to the input of feed-through. We'll do this by right-clicking and then dragging from the output of one to the input of another. And with that, you've completed the setup of your FMU. We can watch the FMU run and see the counter increment on the wiring diagram. We'll also see the model stop around 9 seconds, which is due to a request by the FMU. We'll be able to see this by going into our message log. This next example is to highlight that you can make multiple FMU aspects from the same FMU. On the left here, we've got 2 stare FMUs, and on the right, we have 3 feed-through FMUs. To start, we'll create each instance of the FMU. Once we create the instance, we'll see them populate into the wiring diagram. We can arrange the FMUs in any way we'd like by dragging and dropping. We'll connect the stare FMU to 2 feed-through FMUs, and then from there, we'll connect the 2 feed-through FMUs back to 1 feed-through FMU. Then you're all set to run your model. As the model runs, you will notice the values pass through the feed-through block by looking at the wires. Now that we know how to set up an FMU, let's take a look at an application. What you see here is a vacuum carbonizing system, one that diffuses carbon into iron or steel to make it harder. This is a complex process that requires maintaining vacuum pressure. Modeling gas pressure can be tricky, but with the ability to import models from other simulation packages, we're able to bring in high-fidelity physics to your model with ease. This particular model was brought in from Simulink, which has existing add-ins that help build models for systems like this. When you're happy with your model, you can export it to an FMU within Simulink. With your FMU file, all you need to do is bring it into Emulate 3D and assign it to the correct inputs and outputs. This process will look the same as we did with the previous two FMUs. We'll load the FMU, give it a name, and then create the instance. In this model, I've created custom properties that represent different parts of the system, such as valves, pumps, or pressures. These will all be connected to the FMU using the wiring diagram. As this part is drag and drop, I've sped this up for the sake of the video. To control other parts of the model, like opening doors or closing valves, I'll be using a quick logic routine that I made prior to the video. With the connections complete, we are ready to run the model. You will be able to see when inputs are actuated based on the color of the wire, and you'll be able to see the pressure of the system change with the pressure pump property. The target for this system is less than 4 millibar of pressure. First, we'll add the metal to this chamber, where we'll be able to use a pump to reduce the pressure. For demonstration purposes, I've made the exterior invisible. Notice that as we've modeled this with high-fidelity physics, the gas pressure decreases non-linearly. When the pressure has reached 4 millibar or below, we'll be able to release the metal into the larger system. Another application that benefits from this new feature is web handling. Materials passing through web handling processes have complex dynamics and tension fluctuations. Fortunately, MapleSim offers a web handling library that allows you to model these complex physics. This library was used to create the model you see now. This MapleSim model can then be exported to an FMU and brought into Emulate 3D. In this example, a carriage is controlled with logic's motion to change the distance between rollers. The relevant PLC tags for the motion code were configured as inputs to the FMU through the wiring diagram. With the FMU imported into Emulate 3D, we can see the impact of the motion code on the web tension. The magnitude of the tension is visualized by changing color, blue being the lowest and red being the highest. In the logic, the carriage moves up with an S-curve motion profile and down with a trapezoidal motion profile. Notice how the magnitude of the tension is higher as the rollers move down with trapezoidal motion. This provides us insight into how the motion control impacts our web tension. Thank you for watching, and be sure to check out some of our other feature spotlights for Emulate 3D 2025.